समुद्रवसने देवी पर्वतस्तनमण्डले विष्णुपत्न्यै नमस्तुभ्यं पादस्पर्शं क्षमस्व मे. Those who dare to fly don't care to leave their footprints behind. Welcome to FVS. Good morning, everybody. So we left the previous class at a very interesting moment. Let's resume from that. I hope you are able to see my screen now, the slide.
Yes, sir, it is visible.
Okay, good. So we were, after answering the question related to why composites, and in spite of their disadvantages, which many of which can be overcome through ingenious design, we went into the constituents of the composite, and we are in the process of understanding why fibers. In the rest of today's class, we'll also look at the other question of why matrices. Many of these things I've mentioned in passing while answering some of your questions, as well as in certain other contexts. So all that we'll be doing is kind of summarizing or formalizing those reasons for using a fiber material and a matrix material. So let's go back to the interesting thing that we did last time. We had these four choices of monotonically increasing, constant, monotonically decreasing, and nota, except for a couple of people who were not sure about the choice A because they thought it's towards decreasing fiber diameter, which is why they chose that. But even they, whoever said that it will be different, UTS will change with fiber diameter, boiled down to saying that it would be a monotonically decreasing kind of a trend. So let's explore some of that. So I think you already did this, typing ABCD in the chat window in the previous class, and that's the result that we had. So this in fact answers to a large extent the question why fibers. So the whole purpose of this exercise was to get to that stage to answer this question of why fibers. This is not the only reason, but the UTS versus fiber diameter, or for that matter the Young's modulus versus fiber diameter, are both kind of giveaways in terms of why we have to go for a fiber-like geometry. Now, before I do that, let's also explore what actually is happening when you're actually increasing the fiber diameter. You're moving from what is typically a fiber, by which we mean something which is highly flexible, which means hardly has any bending stiffness, but very high tensile performance. As you keep increasing the diameter of a fiber, beyond a certain point, you no longer call it a fiber. In fact, it becomes a rod. And a rod, as you know, has a finite bending stiffness, unlike a fiber, which has infinitesimally low bending stiffness. The rod has a certain bending stiffness, but then its UTS is known to come down. So why is what we would like to explore in this, and that will then set the platform for using fibers. So what you said was right, many of you at least, that there will be a decrease in the ultimate tensile strength as you increase the fiber diameter up to a certain point. So it is monotonically decreasing, but beyond a certain point, the fall is not much. So if you see the slope of the curve over here, it's a nonlinear curve which changes slope. So initially there is a steep fall, which means very high negative slope. But then as you go, the negative slope tends towards zero. So in other words, it becomes asymptotic at a certain level. So it no longer decreases to any noticeable level. And this is where you are no longer dealing with a fiber, but you're typically dealing with a rod which has a finite bending stiffness, whose tensile performance has come down, but now it is capable of taking some compression as well, which is why it is capable of taking the bending loads, which requires both compressive and tensile performance. So now, in terms of what would happen at the other end, let's see the left end, which is closer to a fiber diameter. Obviously, you can't go for a zero fiber diameter. So there is a certain limit. So in terms of the origin for this, we are not having the fiber diameter at zero over there, because then there is no material, there's no fiber at all. So what are we talking about in terms of the ultimate tensile strength? So there has to be a certain limit that you can go to in terms of reducing the fiber diameter. So can anybody guess what that limit could be? In terms of what is the lowest fiber diameter that you could probably go to?
The molecular dimensions.
Right.
For a chain.
Right. Excellent. Yeah. So if it is a material which involves molecules, yes, molecular dimension. If it's a material which involves atoms, like for example carbon, then it could be closer to the atomic dimensions that you're having, taking into account the chains that it might form through weak bonds, covalent bonds that it might have between those atoms, etc. Okay, so if that is the case, yes, that is right. So what would then be the UTS? Because the way we have drawn the curve, it shows that if we can just extrapolate this to the left end, it kind of goes towards infinity, but that's not the case, right? So we know that there is a limit to the lower level of the fiber diameter. At the same time, there is a limit to what is the maximum value of UTS you could have with a given material. So what do you think that is? What is the maximum value of UTS that you can go to for a given material? What you said is right in terms of the fiber diameter. The maximum value that you can go, minimum value that you can go to is determined by the molecular scale or the atomic scale. But what about the ultimate tensile strength? What is the maximum value that it can have at that value of the fiber diameter?
Bond strength.
Okay, good. So whatever is the bond between those atoms or molecules, so that could determine the ultimate tensile strength, the theoretical maximum that you could have. Rarely is that achieved in practice for various reasons, but that is basically what happens. Now, what about the other end? Suppose I keep extending. I already mentioned that it's kind of asymptotic, but what is it asymptotic to? So as a fiber becomes a rod, what is the value of UTS that this will approach to for a given material?
That will be the UTS of the bulk material.
Excellent. Yeah. So what we typically call as the bulk modulus of that particular material. So if it's carbon, so bulk carbon. If it's glass, bulk glass, etc. Whatever the typical ultimate tensile strength of that is, that's what it would reach. And as I said in the previous class as well, we are just taking the ultimate tensile strength in the longitudinal direction, by which we mean parallel to the fiber direction, as just one example. Most other properties also behave in a similar trend. The actual magnitudes and the reasons for some of these things might vary slightly, but predominantly the reasoning and the trend would be very similar if you plot, for example, the Young's modulus, or let's say the any other properties like shear modulus, etc. So we will focus on a particular material now, so that we will see what happens to that material. But again, this is not material specific in terms of the overall qualitative trends. So let's take glass, for example. So what happens in the case of glass is this. So if you extrapolate to the left end, which as I said, we are not starting at zero, the fiber diameter axis over here. That is determined by what is the atomic or molecular dimensions that are required for any given material. So in this case, the maximum value, theoretical maximum value that it can approach for glass, this is, as I said, this is glass data, but the trends would be similar for other materials like carbon, etc. Some of the reasoning might slightly differ, but predominantly it would be the same. And what is actually happening there, the reason for this kind of reduction that is happening, the apparent reason is the lower probability of failure inducing surface cracks which are generated during the fabrication or handling. So as you go to lower and lower dimensions, what is happening is the number of surface cracks into their sizes divided by the surface area, that starts reducing. So that is what we mean by the crack density, or how much of cracks you have for a given amount of material. That is going to come down as you reduce the fiber diameter, and once the micro cracks associated with the material come down, then obviously it's going to approach what is called as cohesive strength. So in this case, the glass cohesive strength, which is between the adjacent atomic layers that you have, it's an amorphous material, but still there is a certain as you go to lower and lower length scales, there's a certain level of ordering which comes into picture, and therefore there is a certain cohesive strength between the adjacent atomic layers, which starts determining the overall behavior of that fiber itself. So that is what is 11, and it's just to give you a feel for the numbers. On the other hand, the bulk strength of glass is around 0.17 gigapascals. So you see the amount of increase that you have is almost like 100 times of the order of magnitude of 100. So that is the kind of advantage we get in going from a bulk material to a fibrous material, and that's the primary secret behind the success of composites in general and fiber reinforced composites in particular. And it's important that you look at this other term here also. It's not just the fabrication which determines the strength or stiffness, etc. To large extent the strength, but stiffness might be to a smaller extent, is the handling as well. So after it is fabricated, how it is handled can also lead to certain damages at the micro level. So handling that and retaining that in your inventory in an appropriate way as advised by the manufacturer is very important in order to be able to retain what is the book strength or whatever is claimed by the brochures of the manufacturer. So it's the fabrication techniques to a large extent govern the strength stiffness, but handling can, if not done properly, can reduce that. So assuming that's all done properly, this is what the theoretical value is, but that can never be reached in most practical situations. So we're looking at somewhere in between. So that's about 4 gigapascals, where the fiber geometries are now able to harness the large value of UTS, maybe not as large as the cohesive strength, but again compared to the bulk strength, it is far, far more. And what we are plotting is the UTS, but if we were to plot E, you would get a very, very similar trend, and the kind of maximum E that you can harness would also be of the similar kind in terms of where it lies in between the bulk materials Young's modulus and the longitudinal tensile Young's modulus of the of a single atom or single molecule kind of a fiber, what we typically call as whiskers. So whisker is also something used for a mustache, but typically in the parlance of the composites and fiber related parlance, whisker means that it is the lowest dimension that you can go to in terms of the fiber diameter, and so that is typically dictated by the molecular or atomic structure of that particular material, and those have very high strengths and stiffnesses, but it's very difficult to make very long fibers with such small diameters. So the lesser the diameter, the fabrication involved, techniques involved become more and more advanced in terms of the requirements. and in terms of their capabilities start reducing, though over the years it improves, but at any given point of time, let's say at the current technology levels, the minimum diameter that you can go to, and therefore the maximum performance that you can extract out of this is kind of limited, and that is what is called as a whisker. And the whisker's maximum length that you can go to in any given state of the art fabrication techniques is still much smaller compared to the a slightly larger dimension, let's say about 10 microns, let's say, would be much longer fibers that you'd be able to manufacture with the current state of the art compared to the whiskers. So are there any doubts on this?
Sir,
Yeah.
hello sir, good morning, this is Manway. Sir, you talked about crack density. So are you talking about the cracks on the fibers but not on the matrix?
Yeah, right now we are not even including the matrix at all. So we are still not talking of composites. We are only trying to answer the question why fibers, and so we are still talking about fibers. So all these values that we have here are not for the composite but for the fiber alone, which anyway we can't use in an actual structure. So so even this 4 is something that yes, we are able to practically achieve for a fiber but not for a structure, because then it's going to be mixed with a matrix, and that's going to bring this down further.
Okay. Thank you, sir.
Yeah, you're welcome. So the cracks that we are talking about are not in the matrix, because we are not even talking of the matrix now. We are talking of the fiber alone. So we are talking of on the fiber, especially the surface of it, there can be small cracks due to the fabrication techniques as well as due to handling. So, and those cracks may vary in size. They'll be distributed all over the fiber. And if you can have some way of quantifying them, let's say the sum of the lengths of all the cracks which you can observe using non-destructive evaluation, you can actually observe some of these cracks, and then you say the sum of all of these crack lengths per unit volume of this fiber, what is it? So that is basically going to determine how badly it is damaged. And you would rarely find a situation where there is no crack at all. So you would typically have a few cracks. How much less can you go to is the question. And this theoretical value demands that you have a zero kind of a situation, zero crack density. So you cannot achieve that, at least not with today's state-of-the-art technologies. But you can try to approach, especially with whiskers, very close to that value. But the problem is you now have much shorter fibers, and shorter fiber composites are a little less in performance compared to the long fiber composites. And especially if you want to use it for manufacturing processes like unidirectional composites of filament winding, for example, in solid rocket motor cases for missiles or launch vehicles, then you need very long fibers that you're talking about, and so you may not be able to do it with whiskers. So whiskers are still used in short fiber composites, and compared to other short fiber composites of larger diameter fibers, they obviously perform much better. Any other questions related to this? Okay, let's move on. So now that we have understood, I think one more important thing I didn't mention over here. One is in terms of the lower crack density, because of which the fiber properties are going to be much superior. But the other thing is, once we get into the matrix, put this fiber into the matrix, what is going to matter a lot is the surface area of the fiber which is exposed to the matrix. In other words, that interface area plays a critical role as well. So for a given volume, if you have a larger amount of interface area, then you are going to have better stress transfer that is going to take place between the fiber and the matrix, vice versa as well. Now, if you look at cylindrical geometry, which is what a fiber or a rod is, you know that the cross-sectional area is given by pi r squared, where r is the radius of that fiber, multiplied by L will give you the volume of a fiber, pi r squared L. Now, if you keep that in the denominator and look at the surface area which is exposed to the matrix, let's leave out the top surface and bottom surface. It's because it's a plate and we are chopping, so that's not exposed to the matrix anyway. What is exposed is this cylindrical surface. And the circumference is 2 pi r multiplied by L gives you the 2 pi r L as the surface area. Now 2 pi r L divided by pi r squared L, if you cancel out the pi's and the L and also one of the r's, you basically end up with a dependence of 1 by r on the radius. So in other words, it's inversely proportional to the radius. That is, the surface area per unit volume which is exposed to the matrix is going to be inversely proportional to the radius. So once again, you see that what that means is, if you have lower and lower fiber diameter, which means lower fiber radius, you're going to end up with a much more surface area for contact between the fiber and the matrix for a given volume of either the fiber or the composite for a given volume fraction. So all that translates to is, not only are you having the individual fiber performing much better in terms of its strength and stiffness, but also in terms of its ability to transfer the stress to the matrix, especially the shear stress, is going to be much better because it has a much larger surface area over which it's going to execute the same transfer, same amount of stress to be transferred over a larger area, and there, which basically means that it's not the same amount of stress. The amount of stress would come down because the load that would be constant, which is applied on the entire structure. So that load is a constant. So the stresses at the interface would come down, and therefore the probability of the interface failing is also coming down. So in other words, cracks initiating at that region, what we call as the fiber matrix debonding, can also be delayed by going for the lower and lower fiber diameters. So now let's look at a little more formally why the matrix. We have understood very clearly why the fiber. One, because it offers much better strength and stiffness compared to the bulk material. The other is because it has a larger surface area per unit volume. Now what about the matrix? Why is it required? Already we have seen what are the disadvantages of using the fiber alone. So that itself becomes the primary reason why we are going to use the matrix, because now we are talking about a particular component, which is the fiber, which is unable to take compression and therefore bending or shear. It's only capable of taking tension, and it's excellent at doing that. But that's not good enough. We need a structure to take care of all the other types of loads as well. So how do you go about doing that? That's where the matrix comes in. It has far inferior properties in the tensile modulus, tensile strength comparisons with the fiber, but then it provides what the fiber cannot, which is basically the compressive strengths and therefore bending and the shear strengths, all these things, and the stiffnesses as well, and of course the ability to transfer load, so that even if when there is a cut in the fiber or some fibers are damaged, still the stress transfer will take place between one fiber to the other through the matrix. So let's look at the specific reasons to overcome the cons or the disadvantages of using only fibers. One is that the fibers alone cannot support longitudinal compression. They can support transverse compression. Okay, so in other words, if this is a fiber, if I press it, it has a fairly reasonably good compressive strength and compressive stiffness in that direction. What it cannot take is this. So you see an anisotropy in that sense too. Okay, so its behavior is very, very direction dependent, not only in terms of tension compression, but in different directions as well. Its transverse tensile performance is much lower compared to the transverse, the longitudinal tension. But in terms of compression, it's actually much better in the transverse direction compared to longitudinal direction. So it kind of reverses. If you're going from the longitudinal to the transverse, you're actually reversing the relative performance with respect to tension and compression as far as the fiber alone is concerned. So what it cannot support, it's very important to say, is not compression per se, but longitudinal compression, because then it's going to easily bend, because hardly has any bending stiffness, and so it's not going to take that compression. And therefore, because bending involves both tension and compression, it cannot support bending either. The second thing is that poor transverse properties. Except for the compressive strength and compressive stiffness, everything else about the transverse direction of the fiber is bad, whether it's the tensile modulus and tensile strength in the transverse direction or the transverse shear. All of these are going to be poor, and this is going to be provided by the other component, which is the matrix. So this answers the question why matrix from the perspective of fulfilling what the fiber cannot do. Going further, it does a few other things as well. One is to hold the fiber together in a structural unit, and which is why as we discussed briefly in the last class too, now the composite with the fibers in the longitudinal direction and the matrix surrounding it, now if you bring in a compression on that laminate or lamina, you are going to have the ability of the fibers which were earlier not able to take compression in the longitudinal direction, because the matrix is holding them in place. It's not only matrix which contributes to the compressive strength and stiffness now, but the fiber as well, which is held together in a single structural unit rather than as multiple fibers, each of them individually. You would have heard the kindergarten stories in terms of a farmer giving three of his sons a challenge of bending a bunch of sticks. So the son who actually is able to do that is one who can take the bunch off and bend stick by stick, whereas if you try to bend the entire bunch of sticks together, it is much more difficult to do that, if not impossible. So that is what the matrix does in this, the bringing that togetherness of the fibers to make them perform as a single team, as a single unit, structural unit in this particular case. Now, the third function that is important is also to distribute and transfer the stresses, which I mentioned in the previous slide, in terms of the maximizing of the surface area per unit volume, so that there is an ability to transfer the stresses. And this is a very, very important function. There's a lot of interesting mathematics related to that in terms of the differential equations that are there to solve in terms of how the stress varies along the length of a fiber until it is kind of there's a broken end within the structure, and in spite of that, how it is able to transfer the stresses through the matrix to the adjacent fibers, and therefore the effective length of a broken fiber is still around 80 to 90% of its length. It's very, very small ends of that. Again, very similar to what you're talking of in a Saint Venant's principle, but from a very, very different perspective over here. But those equations can be derived beyond the scope of this particular course. We would see that in the analysis and design of composites course. The next function is to protect the fibers from the external damage and environment, because many of these fibers, now that you have it at a very, very small diameter, I said that even a little bit of mishandling can reduce the properties. So that means that they are damage prone, and environment can create a lot of issues with them in terms of their overall performance. But now that you have this covering of the matrix, the most important load bearer of your composite, which is a fiber, is now well protected from the environment. It's not directly exposed to the environment. It's through the matrix that the environment has to affect the fiber, if at all. That can happen over a long period of that particular component, structural component being in service. There can be a seepage of moisture through the matrix. We talked about matrix swelling to some extent earlier. So that can seep in and maybe reach the fiber, and if the fiber is prone to being affected by moisture, it can affect it. Also, if it's a thermal load, Most of these are polymer matrix composites. The polymer is a fairly good insulator, so again it insulates the fibers from that. But beyond a certain point, there will be a level of conduction that is happening through the polymer as well, and the temperatures can become high at the fiber level as well, which is why for high temperature composites, we are not only talking about changing the matrix to a better temperature capable, high temperature capable matrix, but also you're looking at eventually looking at these fibers as well, capable of handling higher temperatures, though they may not reach as high temperatures as the matrix itself, but there can be some of these fibers very close to the surface, so the temperature or the heat can be transferred to them fairly fast. So it's important that they are capable of handling higher temperatures as well. But most dominant temperature handler, just like the compression handler or bending handler or shear handler, is the matrix. So it's kind of underplayed because we always think of reinforcement, that being the strongest, stiffest by a way big margin compared to the matrix as the primary load bearer. But yes, the matrix does many things which the fiber by itself would not be able to do. So this is one of them. The hygrothermal stresses and the ability to protect itself from the damage as well, because the matrix will take the initial damage, and it's only then later that the damage percolates down to the fiber. The next reason why we use the matrix is to provide ductility. So that in this case we're talking of a metal matrix composite. So if you have a fiber, let's say a silicon carbide fiber for example, which is ceramic and therefore very brittle in nature, because it's in a fiber form, it's highly flexible and therefore it can be shaped, but nonetheless it can't take much of an impact etc. by itself. So then you are going to bring in this matrix which surrounds that, which is made out of a metal, let's say titanium alloy for example. Now this matrix, because it's metal, has a level of ductility, and that ductility can be measured in various ways through the ratio of the shear modulus to the bulk modulus, for example, what's known as the Pugs ratio, or it can be measured in terms of the maximum failure strain that you're going to have. So either of which basically leads to the fact that this material can be shaped much better, and also it goes through a certain yield. If you look at the stress strain curve of these composites, it like metals, it goes through an yield, may not be entirely having a huge difference between the yield strength and yield point to the ultimate tensile failure point, but still there is a certain gap which comes in, which is some amount of plasticity that you're building into the entire composite because of the matrix being capable of having an elastoplastic regime. Now, the other important thing is the matrix many times can provide the toughness which the fiber by itself lacks. It could also provide the electrical insulation. Now again, we are not talking of metal matrix but polymer matrix. So again, some of these advantages and disadvantages are common to all matrices, but then some are specific to the type of matrices. So again, that's why the compatibility becomes very important. You have chosen a particular fiber to give a certain required tensile performance in the longitudinal direction in terms of strengths and stiffnesses, but then what matrix are you going to use along with that will depend, one, on the service temperature, as we shall see very shortly, but also depends upon the compatibility between them. And we're talking of compatibility, we are talking of not only mechanical compatibility but also the chemical compatibility. Either it should not react too much, and so that the fiber and matrix completely react with each other and it becomes just one particular compound or more. But what we are talking about here is in terms of there is a certain level of reaction may be actually beneficial sometimes, because then it would just be at the superficial level. So for example, let's say the fiber forms a certain material, let's say a carbide or something, which then becomes a thin coating. That coating, because of this reaction, that coating has formed. Now that coating will become kind of an insulation between the fiber and the matrix and avoid further reaction. So in other words, further degradation. So some level of degradation through chemical reaction might sometimes be allowed between the fiber and the matrix, but more often than not, you're looking at chemical compatibility, meaning there should not be too much of a reaction between the fiber and the matrix materials. But there are these exceptions when coatings can actually be desirable. And sometimes those coatings can also be like, for example, a carbide kind of a coating can sometimes not necessarily be done from the outside, but because of the reaction between the matrix and the fiber, and then can enhance the higher temperature capabilities of that fiber as well. Now, the choice, as I said, one is, of course, compatibility. The second most important thing is the service temperature. So if you're looking at most composites used in primary structures like wings, fuselage, etc., they are not exposed to very high temperatures, and therefore you see the wide usage of epoxy as a matrix, epoxy being a thermoset polymer, and you see polymer matrix composites, or what we call as fiber reinforced plastics, FRPs, being the most commonly used composites in a lot of the primary construction of aircraft structures. So that's what we have here. Other than epoxy, there are many other thermoset polymers as well, like polyester, etc. These typically can go up to 150 degrees centigrade, which is good enough for most applications, and that's the reason why these have been pursued to a large extent across the industry over many decades now, probably close to half a century in terms of the application to the aerospace industry. But then again, there's a wide range of variation within the epoxies itself. There are various classes depending on the manufacturer and their manufacturing processes and the kind of components which go into it, etc. Now, these temperatures again is just given as a kind of a rough numbers. There can be thermoset polymers which could probably go a little beyond this as well. And also, it's also in terms of the two temperatures are involved here. What we are talking of, the service temperature here. The other is during the manufacturing process, what is the temperature that it needs to go to. For example, thermoset polymers, you do not need to take them to a very high temperature, because you can at lower temperatures itself infuse the reinforcement, that is the fiber, into the matrix. But for a thermoplastic polymer, you will need to go to higher temperatures in order to be able to put the fibers in their appropriate places within the matrix. So that might be a little more technologically involved process, and that's the reason why you see the thermoplastics are much lesser used. But now, because of environmental considerations, they are becoming much more essential to be used, because thermoset polymers very, very rarely can be recycled, whereas thermoplastics to some extent can be recycled. Still not as good as with metals, ceramics, etc., but compared to thermoset polymers, thermoplastics are better at the ability to be recycled, because they can be once again reheated and liquefied, and then can be put into various other shapes in order to make other less stringent components out of it, probably for non-aerospace applications, etc. Now, the second category of matrices is also a polymer, but now a thermoplastic polymer. Typically can go up to 425 degrees centigrade. I mentioned polyether ether ketone. Is also nylon. So these are some polymers. But again, there are some thermoplastic polymers whose service temperature can actually be lesser than the that of the thermoset polymers as well. Okay, so I'm only talking of a very, very broad range over here. So don't be too strict about these numbers over here. It looks like a huge advantage going from a thermoset to a thermoplastic in terms of the temperature range, but we have to look at case by case the specific materials involved. But we are talking more in terms of a qualitative sense over there. So there can be exceptions to this rule, that there are certain thermoplastic polymers which whose service temperatures might be lower than that of the thermoset polymers. The third category, which is now picking up, especially for the earlier stages of the aircraft engine, that is the compressor blades or the compressor containment rings, etc., are metal matrices. and these can go way beyond either thermoset or thermoplastic polymers. So it's a huge jump that you have, going all the way up to about 1250 degrees centigrade. So again, this is not good enough at the combustion chamber or beyond, that is the turbine, etc., where temperatures can be much more than this. But it is reasonable, and sometimes you might use metal matrix composites in the turbine as well, especially the after stages, the final turbine stages, where the temperature has come down a little bit, but still could be much higher than this temperature of about 1250 degrees centigrade, because you have active cooling systems. There can be cooling systems, there can be coatings of ceramic kind of coatings on the metal matrix composite, and therefore even though the outer temperature might be higher than, let's say, a melting point of the metal, etc., you might still be able to use it with an appropriate coating and with active cooling systems in place. If you have even higher temperatures, like it is in the case of the turbine blades, etc., you have to go for ceramic matrices. Some examples of that being borosilicate glass, silicon carbide, etc. And these can go 400 degrees more than the metal matrices, up to 1650 degrees centigrade. Again, it varies from material to material. We just having a ballpark value just to understand where they relatively stand. Polymers at lower temperatures, metals at somewhat medium temperatures, ceramic at even higher temperatures is what we are looking at. So even in spite of these higher temperature capability of ceramics, still a lot of the turbine blades, etc., use what are known as nickel superalloys, which are where it's an alloy, but the primary metallic element there is nickel. And these are typically single crystal structures, so you do not have the capability in multiple crystal kind of configuration at the microstructure of the metal to be capable of such high temperatures, because when we say service temperature, we're not only saying that it should be a solid till then, but it should be a solid, and it should be able to maintain certain strength and stiffness until that temperature. Because normally what happens is, as you heat up materials, their strengths come down, their stiffnesses come down. But how much does it come down by? If it comes down by just, let's say, 20-30% up to the service temperature, you might still be able to live with it, because room temperature strengths and stiffnesses are usually much higher. But if the loss in strength and stiffness when heated up to all the way up to the service temperature is still of that order, then it is fine. The other thing is, one, it should retain a large fraction of its strength and stiffness. The other is in terms of its ability to be stable chemically, because at higher temperatures we are not only having a high temperature air coming out, but it's air and the fuel which is burnt, so it's an exhaust which is that they are exposed to, and so there is a possibility of they reacting with those gases and forming certain undesirable materials like sulfides, etc. Whereas sometimes they might form desirable materials like carbides, etc., which, as I said, give a coating and therefore can enhance probably the strength and stiffness. But then again, it should not be such a thick coating that it changes the dimensional stability of that blade, etc. So there is a kind of a give and take over there in terms of their capabilities, in terms of a chemical reactivity also that you need to take into consideration. So it's not purely service temperature and chemical compatibility with the fiber, but chemical compatibility with the kind of environment that it is exposed to. If it's an environment of let's say humid kind of an environment, then obviously the hygrothermal stability becomes important. Now here it is the chemothermal stability that is important in terms of its chemical stability with respect to certain specific gases that are in a large fraction in the exhaust of the aircraft engines. And finally, you have the carbon matrix. which can go all the way up to 2760 degrees centigrade, which is used predominantly in, let's say, re-entry vehicles, etc., which can have because of the hypersonic speeds at which this re-entry might happen, and the atmospheric heating. It's coming from space where there's no atmosphere, eventually enters the atmosphere of a planet, maybe Earth, maybe any other planet, and then that atmosphere, the gases present in that atmosphere can cause a huge amount of heating because of the friction that is involved at such high speeds, and then you need these kinds of materials. So you typically have tiles made out of these kinds of materials, etc. But again, you have to look at the ability of their ability to withstand the reactions with those gases. So whatever, even in the case of the Earth's atmosphere, oxygen can sometimes be a game spoiler in terms of its ability to react with the carbon, etc. So you might have to have some coatings on these. Yes, the material by itself is high temperature capable, but is it chemically also capable of withstanding those kinds of gases which are there in the atmosphere of that particular planet? Those considerations have to be taken into account as well. Are there any questions related to the matrix? Okay, let me move on. The next question that we will answer is, see, learning is a process which is enabled by questions. The more the questions that you ask, not only you to me, but to yourself especially, in terms of a self-study, that is going to really help. Even in an earlier class, I was talking about this Shravana, Manana, Nitidhyasana as unlearning, learning and relearning. All of those processes, when enabled by questions, actually help. So with composites, the question that we already asked and answered is why, and for its components of fiber and matrix also we answered the question why. Now we'll look at some aspects of where these composites are applied in specific applications within aerospace and beyond aerospace as well. So where are composites used? You see some examples of aircraft, launch vehicles, motor casings, could be for missiles as well, satellite applications, etc. But they are finding very large market in the non-aerospace sector as well. So apart from rockets, missiles and satellites, helicopters and airplanes, which are all in the aerospace industry paradigm, many of these composites, even the high performance advanced composites, are now finding a place in other situations as well. High performance automobiles like racing cars, and for generic automobiles, the low performance composites, Young's moduli along the longitudinal tensile direction, less than 100 gigapascals, being less expensive and therefore more available and used in larger scale applications like automobiles. You would have seen, if you are driving on highways, you would have seen these huge long trucks taking these wind turbine blades. They're massive structures, very long, running into sometimes 100 meters or so. So these again, wind energy is something, renewable energy, that is picking up big time in India, especially in states like Tamil Nadu, etc. It's already a huge percentage of the electricity requirement in terms of all the other technologies that are used to produce electricity in some of the northern European countries, the Scandinavian nations, but that's kind of catching up with many other countries as well, taking advantage of the wind energy. And there, the efficiencies of those wind turbines will improve substantially when you're going for lighter materials, which can last much longer, and wind turbines, blades made out of composites, play a huge role there. There are quite a few of those companies which have offices in India as well. There is LM glass fiber, which is now part of the GE, but that's in Bangalore. They work a lot on composites. I typically teach a course on composites to some of their newly recruited engineers, and some of the problems they face are very similar to what we face in the aerospace industry, especially related to helicopter rotor blades. But then some are very, very different as well, because these wind turbine blades can have very large thicknesses compared to most aerospace structures, especially closer to the root, where the blade is attached to the hub. And at these thicker locations, you need to go for what are known as 3D woven composites. So already we talked about weaves in the previous class, plain weaves, satin weaves, etc. Now 3-dimensional weave is basically a weaving which involves a reinforcement in the third direction as well, apart from the surface, so that it's able to take the through the thickness loads, because these transverse loads become substantial in such structures because of the transverse shear, and also because of torsion to some extent that these blades undergo. And the ability to handle that is not sufficient from the matrix alone. So the fiber reinforcement in the third or the thickness direction becomes critical over there as well. And analyzing the 3-dimensional state of stress, because most other airplane kind of structures, let's say a wing skin or a fuselage skin, etc., you can use a plane stress kind of an approximation to start with and get reasonably good results. So it's not a 3-dimensional state of stress, but a 2-dimensional state of stress. But once you go for thicker composites like what are used in wind turbine blades, then you do need to look at the through the thickness stresses as substantial. That is, if you consider the third direction as x3, then sigma I3, where I can vary between 1 to 3, can become as of the same order of magnitude as the sigma alpha beta, where alpha and beta take on the values 1 and 2. So sigma 1, sigma 2, and sigma 1, 2 are all in surface stresses. Sigma, if this is x1 direction, if this is a shell, this is the x1 direction along one direction of the surface. In an orthogonal direction, again within the surface, let's say call it x2 direction. So along x1 and x2 is where you would have majority of the stresses in most thin-walled aerospace structures. That is sigma 1, which is tensile or compressive load in the x1 direction, sigma 2, which is tensile or compressive load in the x2 direction, and then sigma 1, 2, which is basically a transverse shear which is acting on these edges of this shell or plate. Then that basically is also an in-plane shear stress. Now what we are talking about is building the thickness of this. So instead of a thin structure, we have a very thick structure over here. So the multiple layers that you're dealing with. Now the x3 direction stresses, that is sigma 3, which is a normal stress, tensile or compressive, that can be there. Even if the sigma 3 on the top and the bottom may not be very high compared to sigma 1 and sigma 2. In between, it can build up to some level if it is fairly thick. If it is very thin, then the stress gradients do not allow it to become very large in between in a thin kind of a composite. But as you go for a thicker composite, the sigma 3 levels can be substantial as well. And in any case, there is the pressure distribution from the top. And in the case of a fuselage skin, it's not directly exposed, but through the stress transfer, it's exposed to the internal pressurization. So there is a boundary condition of a sigma 3, which is coming from the top and the bottom as well. But even that sigma 3 predominantly causes bending, and therefore the larger stress is the hoop stress, and the longitudinal stress slightly lower than that, but the hoop and longitudinal stresses are much larger than sigma 3 itself. That is the pressure that is applied on the top boundary condition. So sigma 3 in between is also of a reasonably small magnitude. But once you start increasing the thickness, it is possible that there is sigma 3, and one problem with that sigma 3 is that it's a normal stress in the thickness direction, and therefore it can pull apart two lamina if you do not have to the thickness reinforcement, because between two lamina you have a matrix rich region, hardly any fibers, and even if the fibers are there, they are in the transverse direction in which they do not have much of a tensile strength or stiffness, and therefore it can just come apart, or at least partly, what we call as delamination. If it's happening at the edge, we call it as an edge delamination. If it's happening somewhere in between, it's called as an internal delamination. So these kinds of things can occur because of sigma 3,3. But you can also have, and you even in the case of aerospace structures, because of the lift and drag distribution in a wing, let us say, you will have the transverse shear, and that transverse shear will be fairly large in the intermediate layers. And if you have a very thick structure, like in the case of a wind turbine blade, those transverse shears can go to a very large extent. Now what we are talking of is not a sigma 1,2, that is not a transverse shear in this direction, to which the fibers will contribute to some extent, but it's basically you're looking at a sigma 1,3, that is basically it is in this particular direction or this direction you're having a transverse shear, and that is also capable of leading to delamination, because once you have a, let's say, a sigma 2,3 or a sigma 1,3, you also have a complementary shear stress, which is sigma 3,2 and sigma 3,1, and those are going to now create a shear between the two layers. So delamination can occur either because of normal stress perpendicular to the plane of the plates or lamina, but it can also occur because of this shear that is happening between them, which we call as transverse shear, as opposed to in plane shear, which is sigma 1,2, where 1 and 2 are both in plane or in surface directions. Now we are talking of 1,3 or 2,3, which have complementary 3,1 and 3,2, that is on the 3 surface. On the 3 surface, we mean a surface to which the x3 direction is perpendicular, or in other words, the unit vector along the x3 coordinate b3 is going to be perpendicular to that surface. So it's a stress in that direction on that plane. It could be a normal stress sigma 3,3, or it could be a sigma 3,1 or sigma 3,2, and all of these have a capability of delaminating, and therefore you should make there are two ways to tackle this problem. Either you reduce that stress levels, or you increase the capability of the material to take that stress in terms of its strength and stiffness, which is what we are doing here through the thickness stitching. Other ways of doing it would be to, let's say, put certain nanoparticles like carbon nanotubes, etc., in the matrix rich region between the two layers, so that now it's not only the matrix which is trying to avoid that shear or the normal stress, but it is also taken to some extent by the nanoparticles or any other reinforcements that you have in that particular region. The other, of course, is through the thickness stitching. The other is to go for a different matrix, because we know that this is dominated by the matrix. So if you have a better matrix, we chose the matrix purely based on service temperature and compatibility as the primary governing factors. Now if you have a situation where you know that through the thickness stresses, by which we mean the normal stresses, sigma 3,3 and sigma 1,3 and sigma 2,3, if these three stresses are not negligible, then you will choose the matrix also based on that. So for example, a thermoplastic matrix might have better shear properties compared to a thermoset matrix. Again, I'm talking in a very generic sense. There can be a few exceptions to this rule as well, but predominantly you see that. So you can use a thermoplastic matrix, you can use a nanoparticle reinforcement, you can use through the thickness stitching, either one of these or combinations of these, so that you enhance the through the thickness strengths and stiffnesses, and therefore delay or avoid delamination altogether, because this is one of the most common ways in which composites fail. So I just took the opportunity of this particular application of wind turbines, because there you have fairly thick structures there, and therefore transverse loads become very, very critical there. But these takeaways are applicable to many aerospace structures as well. Another application of composites, non-aerospace that is in offshore structures. These are where petroleum is drilled from the ocean. So these offshore structures, many of which are these days increasingly made out of composites because of the high performance requirements for some of these structures, because the loads can be fairly large over there, and you cannot afford to have very heavy structures, and therefore and also in terms of their corrosion capabilities, withstanding capabilities, etc., steel may not be a good enough option in many situations. You might have to go for polymer matrix composites over there. The another application is in terms of containers. You would have seen in ports these massive containers that are there. So apart from the cargo that they bring through the ships, etc., these containers by themselves weigh quite a lot, especially if they are made out of metals. So now there's a trend towards moving towards composites there, so that you have greater strength and stiffness in absolute terms. At the same time, you reduce the weight of the container, empty weight of the container, and therefore its capability to take more of cargo becomes better, because the ship basically is not seeing it as two separate things, that is the container weight and the cargo weight, but it's the total sum of the container plus the whatever is the payload within it, that is going to be considered as the weight that the ship has to take. So if you can reduce the container weight, empty weight, then you can probably increase the payload weight that it is capable of handling, as long as it's strong and stiff enough to do that. And composites are right candidate for that as well, and it's being extensively used there too. The other case is again related to offshore structures, but from offshore structures, how do you pump the oil or gas to the landmass? Because this is happening in the ocean. Now you want to send it across to the landmass. So there can be hundreds of kilometers long pipelines which are going from these offshore structures all the way to the mills where all of these petroleum products, crude products, are processed into refined products like the petrol and gas that we get for our cars and motorcycles, etc. So these pipelines, again, earlier days used to be made predominantly out of metals like aluminium, etc. Over a period of time, their lifetimes have been shown to be much improved if you go for composites. Also, the kind of thermal coefficients of expansion that these metals have over the seasons, that makes these joint designs between pipes. You can't have the entire hundreds of kilometers in a single pipe without any joint. You would have these joints, etc. And now those become kind of weak points, and there can be leakages, and some of these leakages can be disastrous, not only from an economical sense, but more importantly from an ecological sense, in terms of the oil leakages affecting the marine life, etc. So from all of these considerations, there is a movement. This happened quite some time back, about 2 or 3 decades back. I worked with a company called Amaron as a consultant to look at replacing some of their composites, some of their metallic pipes and the pipe joints, especially, which is much more complicated system. The ability to handle temperature changes or hydrothermal stresses, and therefore some kind of a leeway that they should have one pipe into the other. So these joint designs using composites, again the pipe design using composites. So these are all very, very interesting things as well. I've had the great opportunity to work with DRDO as well, quite a few of their labs like ASL, RCI, working on the Agni missile in particular, the second stage solid rocket motor casing over there. When they wanted to go, this is almost 2 decades back, when I wanted to move from a metallic casing to a composite casing. It was not a very simple move over there, because we are not only designing that filament wound structure, but this filament wound structure increases in thickness as you reduce the diameter, because of the way the filament winding process works. And then you have something called the polar boss, which sits over there, and how that polar boss is joined to the the thickened filament wound structure of reducing diameter, you have a cylindrical portion of the solid rocket motor casing, and then a spherical kind of, or nearly spherical kind of a geodesic dome that is over there with an opening for the gases to go out and therefore create the thrust in the opposite direction according to Newton's third law. Every action has an equal and opposite reaction. Now, these structures moving from a metal to a composite was something that worked on in a much earlier stage. I'll also explain a few helicopter applications that our lab has been involved with in terms of composites in the next few slides. The other example we gave in the previous class too was in terms of golf clubs, tennis rackets, bicycles, etc. Many sporting goods where performance requirements justify the inclusion of expensive material. And even where the expensive material may not be affordable, you might go for the lower modulus composites, the basic composites instead of the advanced composites that we talked about in terms of a classification. So you might find glass fiber epoxy kind of composites in many of these sporting goods used by even amateurs, not necessarily professionals. Then electronic industry uses it to a large extent. The printed circuit boards, etc., are made out of glass epoxy. To some extent, it is the E-glass which is used over there, and that's the classification we saw there in terms of E-glass and S-glass in the previous class. So the electronics industry uses a lot of these fiber reinforced composites. Then electrical appliances too, quite a few. If you want to look at weight reductions over there, composites can play a critical role. Sometimes it may not be just weight reduction, but also tailoring it in particular directions where you require greater strength and stiffness. If that is known a priori, which it is for most designs, then you would typically go for a composite to give you fairly large advantages. So now we'll go to some very specific examples that was more generic in terms of the aerospace industry and non-aerospace industry. Now, in terms of specific examples, mostly you would see that even though the aerospace industry has been a pioneer in terms of including composites as primary structures, there is a little bit of conservativeness, especially when related to passenger aircraft, because lives are involved, not only of the crew, that is the pilot and the cabin crew, but also the passengers, and therefore you would typically have a conservative design, and even though certain materials are very promising, may not be used until a fairly long period of their development, because the certifying agencies have to certify them before they can be used. So one of the things that has happened is, even though composites have been used for so many decades, in most applications in the aerospace industry, they used as symmetric laminates. What do we mean by symmetric laminates? If you take a particular thickness of composite and you draw the mid plane of that composite laminate, you go look at the angles of the plies in each layer on the top. Let's say theta 1, theta 2, theta 3, theta 4, etc. If there are 4 layers on the top, at the bottom you would again have theta 1, theta 2, theta 3, theta 4 at the same distance of the same thickness about the mid plane. So what this means is that about the mid plane there is a mirror image. In other words, it is kind of symmetric about the mid plane. There's a mid plane symmetry, and what that eventually brings about, as we shall see in the mathematical equations that we'll derive in a later class, is that there is no coupling between the moment kind of loads and the force kind of loads. In other words, if you apply moments, you only get curvatures. You do not get an increase or decrease in the in-plane dimensions. There's no in-plane deformation. And if you have only in-plane stress resultants, like along this direction you have a tensile or compressive, and shear, then it does not result in any change in curvature, either as a bending curvature in this direction, bending curvature in a perpendicular direction, or as a torsional curvature. It doesn't result. These two get kind of decoupled. It's very easy to do in terms of mathematical modeling, etc. when that decoupling happens. When the coupling happens, still there are fairly well established procedures to do that, but mathematically and computationally a little more involved. That's all there is. So there's not too much of a difficulty in handling that from a computational mathematical perspective, though more effort is involved, but still reasonably well handleable. But more from the perspective of what kind of couplings these result in. I'm trying to pull this structure and it's actually getting twisted, and I'm trying to, let's say, push this structure in a particular way, and it's actually bending in some other direction. So this is what people are not very comfortable with, and which is why you see that most of the applications in aerospace also has been in terms of symmetric laminates. But going forward, if we really need to leverage the full power and potential of the composite, we need to take advantage of some of these. And you'd be surprised, one end fighter aircraft do a lot of this, but even prior to that helicopters did a lot of this. So kudos to the helicopter industry in convincing the certifying agencies that some of these actually work, and that too in primary structures. One example is an anti-symmetric layup. So you could have an anti-symmetric laminate, by which we mean exactly opposite of the symmetric. I told you an example of a symmetric laminate is where you have theta 1, theta 2, theta 3, theta 4, etc. to theta n. And again on the bottom also you go in the downward direction, the same sequence, theta 1 to theta n. Some of these thetas could be repeating as well. In most cases they are. But now, instead of if you have a top layer which is theta 1, then the bottom layer becomes minus theta 1. That is an anti-symmetric laminate. So then again you have the second layer above the mid surface as, let's say, theta 2, then you have a minus theta 2 here. Or for that matter, and again theta 1, theta 2, etc. by themselves could be positive or negative, which means that on the top you could have negative, some of the layers negative, and the corresponding layer here would be positive. So that is what we are talking of only in an algebraic sense, that the negative sign that we are talking about. So that's basically an anti-symmetric laminate. But if you have a 0 degree, then it really doesn't matter, it's plus 0 degree or minus 0 degree. So just 0 degrees would be both a symmetric laminate as well as an anti-symmetric laminate. And so would be a cross ply. If you have a cross ply, because 90 degree also doesn't have, whether it's plus 90 degree or minus 90 degree, again you're going to have just the fibers in the same direction. So a cross ply laminate which has only 0 and 90 degree plies, there the sign doesn't matter. And if you have a symmetry in terms of where you're putting the zeros and 90s about the mid surface, then it again becomes both symmetric as well as anti-symmetric. So the only difference comes when you're having other than 0 and 90 degree plies as well, like 30 degrees or 45 degrees, etc. Again, in that also you see there's a lot of conservativeness in the aerospace industry, though from a purely mathematical optimization point of view, you might get a particular angle. Let's say in the case of a filament wound structure, it might be something like 54 degrees or something might be the optimal. For a very long period of time, they were not willing to go to that. They would go to something close to that, let's say 45 degrees, but not to 54 degrees. But now, of course, things have changed over there. But in major parts of the aerospace industry, still you use typically nothing other than zeros, 15s, 30s, 45, 60, 75, 90. You just go in the steps of 15. You rarely have other angles. But things are changing slowly, but not to the extent that we who work on composites would like it to, because there's so much to leverage from these potential that the composites offer by actually going to other angles and non-symmetric layups as well. So one such example is the anti-symmetric laminate that I wanted to bring across over here, because the anti-symmetric laminate is very interesting, and it's very easy to see just from my demonstration of the fingers over here. Now, if I try to pull this structure towards you, what actually happens is you're applying a tensile load on this structure which has a plus theta and a minus theta. And now what actually happens is some kind of a straightening up is actually happening. When you're trying to pull, the plus theta tends to reduce a little bit towards zero, minus theta also tends to go towards the zero angle. So what essentially that is happening is actually a torsion that is happening. So the even though the applied load is extension, and the major effect of that is an extensional strain in that direction, now there is also going to be a certain small amount of twist that is happening. You have not applied any external mechanical load of a torque. Even though there is no torque which is applied, only an extensional tensile load is applied over there. That is resulting in a not only the change in length of the structure, but it's also resulting in the structure undergoing a small twist. So this is something which happens, as I said, because of the coupling between the curvatures on the one hand, in this case the torsional curvature, and the in-plane loads, which in this case is the tensile load along this particular direction. So this is what we call as an extension twist coupling, which is very classical example of any antisymmetric laminate, what it can provide. If you think of it, see, anything that nature or engineering structures offer can be either a blessing or a disguise. A knife can be used to commit a murder. At the same time, in the hands of a surgeon, it becomes an instrument to save a life as a scalpel. So this dual use of all technologies has been very well known. Nobel was a great example of that when he invented dynamite, and you know what happened, and the Nobel Prize which came out of it eventually for others. So the idea is same way. When you're talking of these couplings, for example, some people see it as a problem, but if you are engineers enough, you can actually see how to utilize it. So you're purposely bringing in this coupling so that you can take care of certain things. So here what we are talking of is, in an antisymmetric laminate, there is an extension twist coupling. Is there some way we can utilize that? The classic example is in the helicopter rotor blade, where you have, because of the rotation at a fairly large RPM, not as large as in the let's say compressor or turbine of an aircraft gas turbine engine, but a reasonably large RPM at which it is rotating creates a centrifugal force. Now, from a structural engineer's perspective, the centrifugal force for that beam, which the rotor blade is nothing but a tensile load. Now, if that tensile load can create certain torsion, can I utilize that torsion? But from an aerodynamicist perspective, what is that torsion? It's actually a change in the angle of attack. Now, if I can tailor the design such that for a given amount of tension, I have a certain amount of torsion, and that torsion changes the angle of attack to the desired levels, so that you are actually having different angles of attack along the length. First of all, due to the way the structure is made itself, may not be a straight structure, it could have a certain pre-twist. So in addition to that pre-twist, the elastic twist that is resulting because of the tensile load, that can also probably enhance and improve the performance of the structure. So this is what we tend to take advantage of, and therefore can we reduce the amount of effort that the pilot has to put in terms of the control stick applications, or in the case of a tail rotor, the rudder pedal applications, etc. Of course, there is also a control system which is involved, which is typically fly-by-wire, and therefore the entire force that is required to change a control surface is not all applied by the pilot. There is some kind of an augmentation that happens before the actuation actually reaches the control surface. But even beyond that, we are only talking about the ability of the structure to utilize some of these couplings in order to have some advantages in terms of better efficiencies, less fuel burn, for example. All of these can be worked out based on this. Same thing holds not only for helicopter flex beams, but also if you look at aircraft propellers, wind turbine blades, and also short takeoff and landing or vertical takeoff and landing tilt rotors. Many of you might be familiar with the Bell Osprey V-22 aircraft, which was one of the pioneers in terms of tilt rotors, where in the cruise condition, these operate like just engines, and then the axis of the engines tilts when you want to fly vertically like a helicopter, which a fixed wing aircraft can never do, unless of course the entire aircraft turns up and you have certain capabilities that are there. Thrust vectoring is also possible in engines by changing the direction of the nozzle, etc. But very simple way in which it was achieved many decades back was by tilting the entire aircraft engine upwards, or the wings that it is mounted upon, so that now you can have either a vertical takeoff and landing, or you can have at least a short takeoff and landing. So you can utilize some of the short runways that are available to us, especially for military applications in areas like high altitude applications like in the Himalayas, in Kashmir, or in the northeastern regions, etc., where some of the you can't afford to have as long runways as you would in some of the ground-based applications in plains. So in these mountainous regions, sometimes you have to work with shorter runways, and therefore the short takeoff and landing is very, very important over there. So all of those tilt rotors there, the flex beams in helicopters, the propellers in aircraft engines, if it is a turboprop, for example, or a piston prop, that is a piston engine driving a propeller, or a turbine engine driving a propeller. All of these you would have seen if you have closely observed these propellers. There's a huge amount of twist that is there. Even in toys, you would have seen many of these small toys, or even in your ceiling fans, you would see a small amount of twist, which actually is a pre-twist. That is, even when it's not operating, the fans are not operating, you see that there is a small amount of twist to enable the aerodynamics performance much better, or the airflow to be much better in the case of a fan. So, and in addition, now if we bring in not only that mechanical twist in the fabrication, but also the material level twist because of an anti-symmetric layup. Now that can aid in addition to the fabricated twist that is built in mechanically. So both these in combination can have a huge potential to improve the efficiency, and many helicopters have actually already taken advantage of this. Okay, sorry, I had this picture, I didn't remember that. So this is the tilt rotor demonstration over here. So you would see that the axis is at a certain angle over here, neither horizontal nor vertical. When it is in the horizontal direction, you're basically having the force coming out of this engine is primarily a thrust, which is increasing the forward performance of the aircraft. And when it is tilted upwards, the same thing is offering a lift, which should have been the function primarily of the wing, but now the engine shares in providing that particular lift as well. And somewhere in between, it's providing both the thrust and the lift, very similar to a helicopter rotor plane, which when it is tilted, the force is always perpendicular to the plane of the rotor, the tip plane of the rotor, and that has a component which is forward, which is thrust, and a component which is upwards, which is basically providing the lift. So I'm loosely using the words upwards, etc. Lift is actually defined as perpendicular to the velocity direction, velocity of the airflow, or the velocity of the vehicle, and drag, of course, in the parallel to that particular direction. But you know what I'm talking about over here. But the whole idea is that you are able to do some kind of a thrust vectoring that is happening over here, whether through the change of the nozzle direction of the aircraft engine, or by actually tilting the entire axis of the engine. You are able to achieve that in all of these, and even in cases where this tilting is not to be done, but the primary force to make you fly is given by a rotating body. Anti-symmetric layups can help improve their structural efficiencies quite a bit, and that's the advantage we're talking about. Any questions on this? Okay, let me move forward. Yeah, so let me go to a very specific example. So this is of the Dhruv, the advanced light helicopter, the tail rotor flex beam. So we just wanted to give this as an example in terms of the kind of complexities which are involved. You would have seen this in many of the cutaways that you probably explored for some of your assignments as well. The kind of geometry is very, very complicated. It's not as complicated as in the case of an aircraft wing, which is a semi-monocoque construction. This is predominantly just the flex beam, which is just a single beam, which is a strip-like beam. So the geometry is not as complicated as that. But once you go closer to the point of attachment with the hub, because this is going to be a hingeless rotor, by which we mean there's no hinge at the joint where the blade is attached to the hub. So it basically uses the flexibility of the blade itself, the bending flexibility or flexural flexibility, as a pseudo hinge, not of zero bending stiffness, but of a small finite bending stiffness. So that's basically what it's using, where it is attached to the swash plate mechanism of the helicopter. Now, the kind of materials that you use will now depend upon what kind of loads that are occurring. And if you look at this sideway picture over here, this is a top plan form view, and this is a sideway view. You see that the thickness is changing as you go along the length, and a large part is a sandwich construction, which is having a core, which we introduced in the stiffness design, where we said that this is a material in between which does not use much of a strength or stiffness requirement, but it's very light, and therefore just pushes up outside the material that is required to take the bending load, so that you have a larger bending stiffness, even though you have very few layers or very small thickness of that. Just because it's farther away from the neutral axis creates a greater moment of inertia, and therefore that's what you have. On the other hand, closer to this, you would have the largest loads, and therefore the material which is used over here, which is glass fiber epoxy, may not be good enough over there. And so though you still have a glass fiber epoxy, in the in-between region you would have certain carbon epoxy as well, to be able to take very large transverse shear loads that are occurring out of that. Next, let's zoom in and look at some of these regions. This is what you see over here. So these darker portions that you see are the carbon fiber epoxy, which is able to take a lot of these bending loads, and the brighter portion, that's what you see as golden yellow, is basically the glass fiber epoxy that you see over there. And you're seeing that there are certain plies which are dropped as you go closer to the root, which is where the largest bending moment is there, and the largest transverse shear load is there. You see the percentage of carbon is increased over the thickness much more than the percentage of glass that you see over here. So that is basically to be able to handle the larger amount of bending loads, and this is what I call as and the industry calls as a flex beam, by which we mean a beam which can flex itself. It has a certain amount of flexibility built into the beam, so it's almost like an elastomeric hinge. You would have seen in some materials like this, where you see there is a hinge over here. It is using its elastic property itself in order to bend at certain locations. So that is an elastomeric hinge. So something like that, but at a structural level, you're talking about by dropping off plies. That, in other words, the number of plies or layers is much more over here. It's fewer layers over here, and that's not done drastically. It's not done in one step, but in multiple steps. You see one ply drops off here, one more ply keeps on dropping off, so that you achieve the final level of thickness here. So in between it appears like it's a tapered beam. So it appears like it's a continuously tapered beam, because there is a matrix which rich pocket which is introduced wherever there is a ply drop. You will find a matrix rich pocket over there to take care of the continuous or gradual decrease, rather than as a stepwise decrease in the thickness. So this is how the Dhruv's tail rotor is actually attached to the hub. So you would see some of the typical dimensions that you go see here. Again, all of these would be different depending upon the overall dimensions of the helicopter rotor blade, the amount of weight, gross maximum takeoff weight of the helicopter, etc. All of these determine these governing factors for this particular design. But what I'm interested in showcasing here is that you do not have the same cross section throughout. The cross section changes. Not in the previous slide, I showed you how it changes with respect to the thickness direction. There is a taper. Now we are showing with respect to the planform direction also, there is an increase in the dimension. That is basically along the chord length, you're having a larger dimension that you have closer to the root than you have in the tip or in between regions as well. So again, the way it is to be attached to the rest of the structure, the hub, through bolted joints and or whatever, so that has to be accounted for there too. Then this is something that we did with the Dhruv. Unfortunately, there was a fatality in one of its prototypes, which led, by fatality I mean the pilot unfortunately died because of that accident during an air show. And the accident investigation there showed that there was some longitudinal cracks which were developing, and it could also be sometimes prone to delamination at the tail rotor level. And so they wanted to have a real-time structural health monitoring system for the tail rotor, which we developed at that point of time. So we introduced certain piezo composites in order to do that, by which we mean the fibers are piezoelectric materials. You would have heard of piezoelectric materials like quartz, etc. Those are conventional piezoelectric materials which are not composites, but now you can have those kinds of piezoelectric materials or a few other ones like lead zirconate titanate, which again comes in various forms. This is a PZT5H. When it is drawn into fibrous forms, and again there are many different ways to draw it in fibrous forms. This technology was initially developed by MIT and later economized or more commercialized by NASA. The way MIT did it was to use an extrusion process where they extrude this ceramic out so that you get circular fibers, which had fairly good performance indices, by which we mean the coupling between the mechanical and electrical signals. So in other words, you apply a mechanical signal, you get an electric output out of it, or you apply an electric field, you get the mechanical output out of it. The first one is a sensor kind of an application. The second one is a actuator kind of an application. So here we are primarily interested in sensing those damages at a fairly initial stage. And so we use these composites in addition to the e-glass epoxy which is already there. We put a outer layer of a piezo composite, now not at the angle at which it was there, but an anti-symmetric kind of a layup at plus 45 on the top and minus 45 on the bottom, so that we are able to sense that twist at a fairly small values. And so when there is a damage, this is going to change quite a bit the extension twist coupling, which we studied through a purely mathematical analysis, highly involved nonlinear analysis, which helped us understand the behavior of these materials. And based on that, we came up with this particular solution, which worked very well. So though a few publications came out of it, what is more important and satisfying for many of us who worked on that problem, especially the students, is the fact that you actually see something which is useful, which is on a flying helicopter today, and hopefully saving a few lives as well, or the helicopters from getting damaged, because the pilot can now get a real-time information in terms of the state of his primary structures like the tail rotor, main rotor, etc. And that gives far more satisfaction as an engineer when you're working on something, to be guided by or motivated by problems which are realistic from the industry, which still have a huge research component in them, and therefore you can publish But at the same time, it's not does not just end with a few papers published and a few people reading it and of no significance to the industry, which is what happens with more than 90% of the papers which are published, unfortunately, not just from India but around the world. So many of you, though you are MTech students, I'm sure that going forward, some of you would be into research. So the reason why I'm specifically mentioning this is the kind of kick we get when we see something that is actually useful for the industry and the society, nations and globe as a whole. That gives us far more satisfaction, and that's what your any work that you take up should do. Of course, at the same time, you enable that you are actually contributing your intellectual capabilities towards coming up with a research which is coming up with new findings. Sometimes academic research can be useful in the longer run. But wherever it is feasible to combine academic research with actually practically feasible applications at the earliest possible time, actually is like what you call as getting two mangoes with the same stone. You hit a stone and try to get two mangoes with it rather than a single mango. That is basically what you try to accomplish, and that's what should be the motivation of most researchers. There is always room for some people to engage in purely academic research, keeping very long-term goals in mind, or some people to do just pure consultancy where no research publications or of any kind are coming out of it. You just apply the existing body of knowledge to routine problems, and those are very important as well. But it's the in between that is quite exciting, because you're touching the possibilities of both these ends, and that's where most people who do masters and PhD typically end up with. May not be in aerospace industry, but wherever you are, eventually I think those kinds of problems are the ones which you are proud of at the even probably at the end of one's career. So with this, I'll probably stop today's class. In the next class, we'll take up this most important topic of modeling structures, which is what the core of this course will be in terms of understanding how we will model structures, both of made out of metals as well as composites. So we are going to introduce it in a generic fashion, so that a specialized version of this will be applicable to metallic structures as well. Of course, we will not be dealing with the plastic regime, etc., which metals and metal matrix composites would be required to handle beyond a certain level of loading. Keeping that aside, at least in the typical operation regimes, how to model these structures when they are still in the elastic regime. Many of the takeaways from a generic model will be applicable both to composites as well as metals, and which is the approach that we shall take, very closely following your textbook, which is C.T. Sun's book from Purdue University on the mechanics of aircraft structures. So with this, I conclude my lecture. If there are any questions based on today's class, I'd be very happy to answer that.
So,
Yes.
sir, why wind turbine blades are thick composites? Why not thin composites along with the stringers and spar webs?
Yeah, good question there. See, the thing is that you as you go to these thicker composites, what happens is the ability to handle this with the thick composite was a big issue when you're having it on a flying aircraft, because its performance now depends upon the overall weight. Now here, the weight is not as much a consideration. Yes, because it is a moving structure, you still have certain weight consideration, which is why in the first place you go for composites. But now you're willing to live with a thicker shell at the root rather than go for a semi-monocoque construction, which is going to further complicate the overall design. So that has been the approach that the wind turbine blade industry in particular has taken up in order to do this. But you're absolutely right that an alternate design option is definitely there, where you can go for a semi-monocoque construction, where you can have still a thinner shell and go for these stiffening structures, and there you can probably avoid a lot of these delamination issues that they are encountering right now, without having to go for 3D woven composites. So these are just two design paradigms where it is absolutely essential to have the overall component weight come down, so that the overall vehicle weight has to come down in a moving structure. There you had no choice but to go for a semi-monocoque construction for larger, faster aircraft. But here you have a choice whether to continue with a thicker monocoque construction or a semi-monocoque construction, and most of the wind tunnel blade industry has gone the way of the monocoque construction. There are probably other reasons to it, which I'm not privy to.
Okay, so thank you.
Yeah, welcome, Samvai. Anybody else? Any questions? Okay, then thank you. I'll see you next Tuesday. Take care. Bye-bye.
मृत्युंजय मंत्राः
त्र्यम्बकं यजामहे सुगन्धिं पुष्टिवर्धनम् उर्वारुकमिव बन्धनान् मृत्योर्मुक्षीयमामृतात् एते सहस्रमयुतं पाशा मृत्योर्मर्त्याय हन्तवे तान् यज्ञस्य मायया सर्वान् वयजामहे मृत्यवे स्वाहा